Great. So thanks very much to the organizers. First of all, Monica, Angela, and Miles for the invitation to speak. And thanks to all of you for being here today, wherever you are in the world. I was getting ready to give this talk this morning, and I was thinking about when I gave a talk at the Mittag-Leffler Institute. I don't know if any of you have been there, but it's a lovely place where you do not wear shoes inside. And so all of the visitors are told this in advance so that you can bring slippers or house shoes if you want. And when I gave a talk there, I said during the talk that this was the first and perhaps the only time I will ever give a seminar in my slippers. It turns out that that was false, because I am currently also not wearing shoes. So that was sort of amusing to me. But anyway, okay. So let me just start by saying that, so this talk is about spectral stability, the Maslov index, and spatial dynamics. Oh, sorry, there's an extra S up there in the title. But if any of you don't know what any of those words mean, hopefully it will become clear as the talk goes on. And I want to mention upfront my collaborators. So I will mention people's names at sort of the most relevant points in the talk. But I wanted to list everyone up here because this is really sort of about a collection of projects that have involved a group of people. And I also want to mention AIM, the American Institute of Mathematics. They have this really nice program called the Squares program, where you can get a small group of people to meet for 1 week during the summer for 3 successive years to work on a project or group of projects. And so much of this work sort of came out of that a square at AIM that I did with a subset of the people that you see listed here. Okay, so oops. Okay, so let me just start with some motivation. This might be familiar to many people. It's relatively basic. It's just sort of Sturm-Liouville theory. But I want to go through it sort of carefully because I think that much of the intuition for what will follow is present even in this very sort of relatively simple setting. Okay, so what we have here is a second order eigenvalue problem on a bounded interval with Dirichlet boundary conditions, 0 Dirichlet boundary conditions. So we want to understand the spectrum of this operator. And one way to do this is by defining what are called proofer coordinates. So they're basically polar coordinates for u and its derivative. So instead of considering, you could sort of write this second order equation as a first order system in a sort of standard way by considering u and u prime and looking at the resulting two-dimensional phase plane. But rather than writing it as a first order system in that usual way, we will instead use the variables r and theta. And this is useful because of the following observations. So if you look at the resulting equations for r and theta, the first thing you notice is that the equation for theta decouples. So there are no r's anywhere in the equation for theta. And then if you look for a moment at the equation for r, what you see is that the set where r is equal to 0 is invariant. Which of course, if r is 0, then we have a trivial solution. So if we're looking for eigenfunctions, we want a non-trivial solution. So the only way to have a non-trivial solution is if the angle theta is causing u to be 0. And since u is defined to be r sine of theta, that will happen exactly if theta is equal to an integer multiple of pi. Okay, so the values of theta and whether or not theta is an integer multiple of pi will sort of control whether or not u is satisfying the Dirichlet boundary conditions. Okay, and then the third observation I want to mention right now is that if you look at the equation for theta, if lambda is very, very large and negative, then the right-hand side of the equation for theta will be positive, and so theta will be forced to oscillate. So theta will be forced to increase, and so solutions will be forced to oscillate. Okay, so what this means, so again, because the equation for theta is decoupling, we can sort of ignore the equation for r for the time being, focus only on the equation for theta. And then to ask if lambda is an eigenvalue, we can say, okay, let's suppose that at our left edge of the boundary, we start at theta equals 0, so the Dirichlet boundary condition is satisfied. We think of that as our initial condition, and then we flow forward in x, and we ask where theta lands when x reaches b, the right edge of the interval. And then we ask whether or not theta lands on an integer multiple of pi. If theta lands on an integer multiple of pi, then that means both of the Dirichlet boundary conditions are satisfied, and so we have an eigenvalue. So here in this picture, I've plotted an example of an eigenfunction. So this is a solution that satisfies the zero boundary conditions at the ends of the interval. And then here would be the corresponding dynamics for theta. So we would start, say, at 0. We would go around. When we complete one half rotation, that's when we reach the first 0 of the function. Another half rotation, we reach the second 0. And then the third half rotation, we end up at our 0 Dirichlet boundary condition at B. Okay, so basically because of the properties of the system, we can understand the eigenvalue equation and the spectrum of the operator entirely by just focusing on this scalar equation for the dynamics of the angle theta. So this is very powerful, okay? So if we think about what this means, okay, so again, we're thinking of the value of theta at A as our initial condition, and we're flowing forward to see if we land in an integer multiple of pi. And we see that when lambda is very large and negative, theta is forced to oscillate, so there's going to have to be an eigenvalue somewhere there. So let's fix such an eigenvalue and call it lambda k, and let's label it to indicate that it is an eigenvalue such that at x equals b, theta lands on k plus 1 multiples of pi. Okay, and then what you can do is you can play this game and you can think about what happens as you continuously vary the eigenvalue parameter lambda. So here at our eigenvalue lambda k, we land on k plus 1 integer multiples of pi. And then as we increase lambda, we do not have an eigenvalue because the value of theta at b is also going to change continuously until we get to lambda k plus 1, which is the value where we land on k pi, and so forth. And so in this way, we generate this discrete sequence of eigenvalues that stops at some largest eigenvalue lambda naught. And that's the value of lambda where theta has sort of just enough time to complete one half rotation. And for larger values of lambda, we then know we cannot have any more eigenvalues because theta is no longer able to complete a half rotation or more. Okay, so here's again, I've just rewritten the equation and redrawn this picture of the eigenvalues and the values, the integer multiples of pi where theta lands. And then here's the corresponding picture again. So this is the picture I drew before with our eigenfunction u. This function has 2 zeros in the interior of the domain. This corresponds to the eigenvalue lambda 2. So lambda 2 means that theta lands on 3 pi at B, and so we complete 1, 2, 3 half rotations. And so this is the idea for understanding eigenvalues and eigenfunctions in terms of tracking the oscillation of this angle theta. And this has important consequences for stability. So for example, if you were to consider a scalar reaction diffusion equation, and suppose you had some stationary solution that I'll call phi, and you linearize around that stationary solution and you consider the corresponding eigenvalue problem. Now this is exactly the same as the eigenvalue problem I showed you before, except I'm cheating a little bit because before we had a bounded interval as our domain and we had Dirichlet boundary conditions, whereas now I'm considering the problem on the entire real line. And so rather than boundary conditions, we have to sort of specify our function space. So you can specify, for example, L2. But I guess I'm just going to ask you to trust me that the theory still works in a very similar way, even on the infinite line. Okay, so we have this eigenvalue problem. And what you notice is that if phi is a stationary solution, you can take a derivative of that equation to see that phi prime has to be an eigenfunction associated with the 0 eigenvalue. And this allows you to count unstable eigenvalues by counting zeros of phi prime. So in other words, if phi is a pulse, so suppose phi looks qualitatively like the left side of this picture here, well then its derivative is going to look like this and have exactly 1, 0. So if phi prime is an eigenfunction with exactly 1, 0, relative to our labeling from the previous slide, that means phi prime is the eigenfunction u1, and its corresponding eigenvalue, which is 0, must be the eigenvalue lambda 1. So that means it is not the largest eigenvalue, and there in fact has to be a strictly positive eigenvalue lambda naught. So that means if there's a strictly positive eigenvalue, that means that this pulse is spectrally unstable as a solution to the reaction diffusion equation, which also means in the symbol context it's going to be sort of unstable more generally in a nonlinear sense. Okay, so this Sturm-Liouville theory is very powerful. It allows you very quickly to determine the instability of any pulse solution for a scalar reaction diffusion equation. And we are effectively just using the zeros of this eigenfunction as a proxy for the eigenvalues. So rather than analyzing the eigenvalues directly, we're just analyzing the zeros of the eigenfunction. Okay, so there's a related concept that's important, and it's the concept of conjugate points. So let me explain to you now what a conjugate point is. So here I have my same equation for the angular dynamics theta. Previously, we had fixed the domain to be the interval a, b, and then we were varying lambda. Now we're going to switch our perspective and fix the eigenvalue parameter lambda and instead vary the spatial domain. So lambda is going to be fixed, and we consider the spatial domain to be the interval as. And S is a parameter that lives in the sort of maximal domain. And again, we have this perspective where we start with an initial condition where theta is equal to 0 at A, we flow forward, and now we see if at the right endpoint, which is now S, if theta lands on an integer multiple of pi. If it does, we call S a conjugate point. So we can fix lambda to be any value we want. So let's fix it to be an eigenvalue. And in particular, let's fix it to be the eigenvalue lambda k, so that we know if S is equal to B, then our angle theta would be landing on k plus 1 multiples of pi. Then we can play a game similar to what we did before. So when S is equal to B, we have a conjugate point that I'm going to label sk because we land on k plus 1 multiples of pi. If you then slowly decrease the size of the domain, so in other words, theta now has less time to oscillate, you don't get an eigenvalue again, or a conjugate point again, until you land on the value sk minus 1, which is exactly when theta lands on k multiples of pi, and so forth. And you continue in this way to get your conjugate points sk down through s naught. Okay, and the process stops at S naught. That's the smallest conjugate point, because after that point, theta no longer has enough time to complete half a rotation. So in this way, we sort of get this correspondence between eigenvalues and conjugate points. So this relationship between eigenvalues and conjugate points is often depicted in what we tend to refer to as the square. Okay, this is not a technical term. This is just what we tend to call this picture. So here I've plotted on the horizontal axis is lambda, the vertical axis is S, the conjugate point parameter. And then you draw this box. So if you look for eigenvalues sort of between lambda star and some very large value lambda infinity, then there's this correspondence between the eigenvalues that you find in that interval and then the conjugate points that you find in your spatial interval when lambda is fixed to be that smallest value lambda star. Okay, and in this simple case, the simple scalar case, it's sort of relatively easy to see this correspondence between eigenvalues and conjugate points. I'm drawing the full square here and mentioning that when lambda is large, equal to lambda infinity, you can check that there are no conjugate points. So if you were to consider this side of the square, there would be no conjugate points. And if you were sort of to collapse your domain entirely, you would also see that there are no eigenvalues. Later, when we have a more complicated setting, it's going to become important to consider the entire square in total, because we're going to want to use a topological argument. And so we're going to want to think of the square as a sort of a trivial loop in the plane, and that's going to be important later. Okay, so we have this square, and what the square is sort of illustrating is the fact that the number of conjugate points for lambda fixed at lambda star is equal to the number of eigenvalues that are strictly greater than lambda star. So if you want to count eigenvalues, you can do that instead by counting conjugate points. And if you're interested in detecting instabilities of, say, a solution that you've linearized around, then it is convenient to fix lambda star to be 0, because then the number of conjugate points corresponds to the number of positive eigenvalues or the number of unstable eigenvalues, which some people refer to as the Morse index of your operator. I should mention that there's a convention choice here. Sometimes people think of the Morse index of an operator as being the number of negative eigenvalues. I'm thinking of it as the number of positive eigenvalues because I'm interested in detecting instability. So I want to count positive eigenvalues rather than negative eigenvalues. And so this is a simple case of what is often called the Morse index theorem. And it goes back to the 50s to the work of Morse and Bott and other people. And I just also want to mention one thing that was really important in this argument is there was sort of a monotonicity in both the parameter lambda and in the parameter S. In other words, as we varied either lambda or as we varied S, the amount of oscillation in theta changed in a monotonic way. For one of the parameters, it changed in a negative way, and for the other parameter, it changed in a positive way. So that monotonicity is going to come up again later. Okay, so just to summarize what we've done so far. So Sturm-Liouville theory, when it applies, is very powerful in scalar reaction diffusion equations. It allows us to conclude that pulses are unstable. We don't need any details about the equation or the underlying wave. We just need to know that it supports a pulse solution, and then we immediately can conclude the pulse is unstable. Similarly, you can conclude that a monotonic front is going to be spectrally stable. And in general, finding eigenvalues of an operator is very hard. And so the advantage here is that finding conjugate points can be easier. So in this simple scalar case, all we had to do was count zeros of the eigenfunction at 0, which was the derivative of the wave. And again, in this scalar case, conjugate points can be analyzed via the winding of this phase, and the monotonicity in lambda and S was key. So the question then is, can we generalize this to systems of equations, or can we generalize this to multidimensional domains? So let's start out by considering systems. So I'm going to focus on this system of reaction diffusion equations here, and I'm going to make a sort of key restrictive assumption, which is that the nonlinearity f is the gradient of some function g. This is going to imply that when we linearize around a solution of interest, that linear operator we get is self-adjoint, and it's also going to give us a symplectic structure, which is going to allow us to generalize the notion of this angle theta to n dimension, or 2n dimensions. Okay, so so we have this reaction diffusion equation with this sort of gradient structure in the nonlinearity, and let's assume we have a stationary solution phi, and let's assume it's a pulse. So in other words, its limits at both plus and minus infinity are the same and given by some vector phi infinity. And then we consider the eigenvalue equation, which is what we get when we linearize the PDE about the solution phi. And I'm going to make another assumption, and I'm going to call this a natural assumption. I'm going to assume that the essential spectrum of this operator L is stable, which is equivalent to making the assumption that this matrix, the Hessian of G evaluated at phi infinity, is negative. I say this is a natural assumption as opposed to the restrictive assumption that I mentioned before, because so you can generally divide the spectrum of L into two sets, the essential spectrum and the point spectrum. The essential spectrum is typically very easy to compute. And if you're interested in detecting instabilities, if the essential spectrum is already unstable, you've sort of already detected an instability and you're sort of done. So the interesting case is then when the essential spectrum is stable and you want to understand if there are any instabilities in the point spectrum. So that's why I refer to this as a natural assumption. And this assumption will come up later. Okay, so here I've just rewritten our eigenvalue equation. And so if you write it in a first order, as a first order system, this time in sort of the natural way where you let u prime equal v, and then v prime has whatever the corresponding equation is, what you get here is this system in R2n. And I'm going to write it in a particular way. I'm going to write the right-hand side as the product of two matrices. The first matrix is this J, which is sort of going to define our canonical symplectic form. And then this matrix B, which because of the assumption that the function f was a gradient, this matrix B is a symmetric matrix, and that will be important later as well. Also, because of this assumption that we've made about f being a gradient, the spectrum of L is self-adjoint, and so the spectrum of L is real, and so we can assume that lambda is a real eigenvalue parameter. Okay, so can we develop something like a Sturm-Liouville theory for this sort of eigenvalue problem? So it turns out that some time ago, Arnold generalized the notion of phase to Rn via the Maslov index and proved some oscillation theorems. So we are going to use his concept of the phase via the Maslov index. So then it remains to ask if we can connect these oscillation theorems and this notion of a phase with eigenvalues. And so the answer is going to be yes. And I also just want to mention that this perspective here on this slide is an example of what is often called spatial dynamics. So we have the second order eigenvalue problem in the spatial variable x, but we write it as a first order system, and now we're thinking of x as sort of like a time-like variable. So this is also what we were doing with the phase theta in the context of Sturm-Liouville theory. And we, you know, there was this nice analogy to think about how much time theta has to oscillate as we changed the length of the domain, etc. Okay, so this is all that is meant by the term spatial dynamics, is just thinking of a spatial variable as a time-like variable. Okay, so let me sort of leave our eigenvalue problem for a moment and just talk a little bit about the Maslov index and the idea of oscillation in higher dimensions. So so these next couple slides are not specific to what I've been talking about before. So if you have a symplectic form on R2n, defined, for example, through this matrix J, then you can define what's called the associated Lagrangian Grassmannian. So this is the set of all n-dimensional subspaces in R2n on which the symplectic form vanishes. And each Lagrangian plane has an associated frame matrix. So this means the plane L can be written in this form. So you have two n by n matrices A and B, and basically the range of this matrix is the subspace L. And sometimes we sort of just write the frame matrix AB in place of L, with the understanding that this is what's really meant here. And of course, the Lagrangian structure and the fact that L has to be Lagrangian places some restrictions on the matrices A and B. A and B can't just be sort of any n by n matrices. They have to satisfy some conditions that are equivalent to requiring that L be Lagrangian. I'm just not bothering to write down those conditions. Okay, and so suppose we have a path of these Lagrangian subspaces for some path parameter t in some interval. And suppose we're interested in detecting intersections of this path of Lagrangian subspaces with a fixed reference plane, such as what's called the Dirichlet plane. So the reason this is called the Dirichlet plane is, for one reason you could think about this, is if you think of the two entries in this vector as like u and u prime, then setting u equal to 0 is equivalent to thinking about a zero Dirichlet boundary condition. Okay, so having this path of Lagrangian subspaces and looking for intersections with this Dirichlet plane, not necessarily at the boundaries of our domain, but maybe somewhere in the interior of the domain, this is very similar to the idea of looking for conjugate points, which is what we did in the case of Sturm-Liouville theory. Okay, so we have this path. We can associate a path of frame matrices with the Lagrangian path. And then what Arnold showed is that there's a well-defined angle phi that satisfies this relationship here. So the reason why this works is so this the matrix in the brackets here that I've called W, it turns out that because of the Lagrangian condition, and which implies certain things about the matrices A and B, that leads to the fact that W has to be a unitary matrix, and hence its spectrum is on the unit circle. This is sort of intuitively why it makes sense to define this angle angle phi. Okay, and one can also prove that the dimension of the kernel of W plus the identity is equal to the dimension of the intersection of the Lagrangian path with the Dirichlet subspace. Okay, so in other words, what this says is that So then what the Maslov index is doing is it's counting with multiplicity and direction the number of times an eigenvalue of the matrix W crosses through -1. Okay, because notice if W has an eigenvalue of -1, then this kernel is going to be non-trivial, and so this dimension count is going to be non-zero, and that then implies over here on the right that you have a non-trivial intersection between your path and the Dirichlet subspace. Okay, and it turns out that the Maslov index is counting exactly this eigenvalue through -1, so it's exactly sort of telling you something about the dimension of this intersection. And the fact that this works is related to the fact that the fundamental group of the Lagrangian Grassmannian is the integers. So you can think of this count as being something like a winding number count. And if your path L of Lagrangian subspaces happens to be a loop, then the Maslov index is just its equivalence class in the fundamental group. Okay, so this is sort of the intuition behind how we are able to define an angle, a meaningful angle in R2n that allows us to count things via the Maslov index. Okay. So let's come back to our eigenvalue problem. So here is the problem we want to understand. This assumption we made about the Hessian of G being negative when evaluated at the end states of the pulse implies that if we evaluate the right-hand side at the end states of the pulse, we're going to get this matrix here. And that matrix is going to be hyperbolic with stable and unstable eigenspaces of dimension n. So in other words, if we consider the asymptotic eigenspaces, the stable and unstable eigenspaces at plus and minus infinity, and sort of flow them forwards and backwards respectively, we're going to get subspaces that always have dimension n. So here's a picture. So again, I've just rewritten the equation. So at minus infinity, we can decompose R2n into the unstable subspace and the stable subspace, sort of add the asymptotic matrix, similar at R2n. And the sort of classical way to think about an eigenfunction would be that you need, since we're working in L2, we would need our eigenfunction decay to 0 at both ends, plus x equals plus and minus infinity, which means as we go forward to plus infinity, our solution would need to be asymptotic to the stable subspace so that it's decaying. And at minus infinity, our eigenfunction would need to be asymptotic to the unstable subspace so that it's decaying in backwards time, backwards x time. Okay, and so then you would have a non-trivial eigenfunction if and only if you have a non-trivial intersection between these two subspaces, the unstable subspace that comes from minus infinity and the stable subspace that comes from plus infinity. That would be the classical way to think about eigenvalues and eigenfunctions, but we're going to take a different perspective and utilize the fact that it turns out that both of these subspaces, EU minus and ES plus, they're both paths of Lagrangian subspaces where you can consider either X or lambda to be your path parameter. So instead of looking directly for eigenvalues and eigenfunctions, we can instead look for conjugate points. Okay, so I'm going to define my path of Lagrangian subspaces to be the unstable subspace coming from minus infinity. And I'm going to ask, when is that unstable subspace? When does that unstable subspace have a non-trivial intersection with the Dirichlet subspace? Okay, that's the definition of conjugate points in this higher dimensional setting. And the main thing that we were able to prove is, so I'm not going to state the theorem with sort of all the technical details. The main thing we were able to prove is that we have this same square picture from before. So you draw your square. On the horizontal axis, you have your eigenvalue parameter lambda. On the vertical axis, you have a sort of a conjugate point parameter S that sort of controls the shrinking of the spatial domain. And what you can prove using a sort of topological argument involving the Maslov index is that the number of eigenvalues that are strictly bigger than 0 is equal to the number of conjugate points when lambda is fixed to be equal to 0. Okay, and again, so it looks a little bit, this picture looks a little bit funny because our spatial domain is infinite. So this vertical axis is somehow like the infinite axis, but I've drawn this square as if it's finite and bounded. Okay, so there's a little bit hidden in this picture, but the basic idea is the same. So so let me, yeah, here we go. Okay, so here's a couple comments about the proof. So the first thing you have to do is just compactify your spatial domain so that this really does become a bounded square. Okay, and then you have a path of Lagrangian subspaces that goes around the entire square that comes from this unstable subspace at minus infinity. And since the square, the boundary of the square in R2 is a trivial loop and it's contractible, that means that the Maslov index of this path around, which is a loop around the entire square, must be 0. Okay, and so then you can think about computing the Maslov index on each of the pieces. If you can show there are no eigenvalues at the bottom and no conjugate points on the right. And then you can use a monotonicity argument to prove that all of the eigenvalues at the top contribute negatively to your Maslov index. All of the conjugate points on the left contribute positively to your Maslov index. And since everything must sum to 0, you know that that means that the number of eigenvalues is equal to the number of conjugate points. And I also just want to comment that we don't, to prove this, we don't use the Maslov index and sort of that angle phi and the matrix W that I showed you on a couple slides ago. Instead, what we use is the characterization of the Maslov index via what's called the crossing form from some work of Robin and Salomon. So we use a slightly different way of thinking about the Maslov index, but I find that for introducing the idea of a Maslov index, that sort of other way that I showed you is, at least for me, more intuitive, which is why I sort of presented that other perspective. Okay, a couple additional comments about this. So in addition to proving the square, the other thing that we were able to prove is that, again, in this case, system of reaction diffusion equations where the nonlinearity has this gradient structure, we were able to prove that it is also true that a pulse has to be unstable. So we use some sort of symmetry argument to prove there has to be at least one conjugate point and thus at least one unstable eigenvalue. And I mean, I find this aspect of the result particularly important because although there are many theoretical results at this sort of recent theoretical results at this point that connect the Maslov index to unstable eigenvalues via these conjugate points, connect unstable eigenvalues to conjugate points via the Maslov index, there are very few applications of these results to actually determine stability or instability of a given solution to a given equation. Okay, so this is sort of notable in that we were actually able to apply this result in a useful way. And I also want to mention that I have a current project with Jonathan Jaquette that is to work on understanding how to use validated numerics to count conjugate points. So the idea is that if you wanted to sort of investigate stability numerically, and in particular, if you want to do it rigorously using numerics, if you're going to do it via an Evans function computation, so this is maybe a comment for people who know about the Evans function. If you want to do it via an Evans function, you have to compute a winding number, do a winding number calculation with the Evans function around an entire contour in the complex plane. And that's very computationally intensive. Whereas this method, because you just have to look for conjugate points for a single fixed value of the eigenvalue parameter at 0, it's much, much faster and more efficient. Of course, it requires that your equation have this symplectic structure, so it doesn't apply as broadly as the Evans function does, but when it does apply, it's much faster. Okay, so that's how we generalize the result to systems of equations, but still with a scalar spatial domain, a one-dimensional spatial domain. So the question is now, can we generalize this to multiple spatial dimensions? So here's an eigenvalue problem in multiple space dimensions, again, with 0 Dirichlet boundary conditions on the boundary of the domain. So can we develop anything like a Sturm-Liouville theory here? Can we define a notion of conjugate points? Is there a Lagrangian structure? Is there a Maslov index? And the answer is yes, and to some extent. The way we get at this idea of conjugate points is to sort of use a shrinking family of domains that was sort of introduced by Smale in the 60s. Okay, so we have in blue is the original spatial domain, which I'm going to label omega 1, and we can shrink it using a parameter s. So these red domains are the shrunken domains, and we shrink it down to a point, which is omega naught. And you can use this to define a path of subspaces. So my path parameter is going to again be S and lambda. And so what I do is I take a solution to the PDE without any reference to any boundary conditions at all. So just is the PDE satisfied on the domain omega S. Okay, and then you evaluate the solution and its normal derivative on the boundary. Okay, so it's kind of like considering the trace of the solution on the boundary. Okay, but again, no reference to boundary conditions. And then you again define your Dirichlet subspace in much the same way as before. So you require the Dirichlet subspace is a set of solutions that are 0 on the boundary, but the normal derivative is not necessarily 0. Okay, and then you want to ask, so conjugate points are intersections between this path of subspaces and the Dirichlet subspace. And the way you give this a symplectic structure, so I haven't said anything about a Lagrangian Grassmannian yet, the way you give this a symplectic structure, okay, so here's the sort of ambient Hilbert space that is relevant for evaluating the solution on the boundary and its normal derivative on the boundary. And then the symplectic form is defined through, so this angle bracket here, this is the dual pairing between h1/2 and h-1/2. So this is sort of a standard way to define a symplectic form on this Hilbert space. And in infinite dimensions, it turns out that you don't want to just talk about the Lagrangian Grassmannian, you want to talk about the Fredholm Lagrangian Grassmannian. So there's an extra Fredholm condition in the definition that is important, but I'm not going to get into it. But it turns out that both this path of subspaces and the Dirichlet subspaces live in the Fredholm Lagrangian Grassmannian. And so you can use this to develop a machinery to relate conjugate points to eigenvalues via the Maslov index. So this is not work that I've been involved with directly, but it is work done by Deng and Jones and also Cox, Jones, Latushkin, and Sukhtayev a few years ago. Okay, so the last thing I want to mention is that this interesting work about how to generalize this relationship between unstable eigenvalues, conjugate points, and the Maslov index, it suggests a way to think about this concept spatial dynamics I mentioned earlier in higher space dimensions. So suppose you want to understand solution to, say, this elliptic equation here. You can again consider this shrinking family of domains defined through some parameter S. And it is helpful to sort of think about this shrinking using some sort of family of diffeomorphisms. And then you can define the boundary data in the following way. So F is going to be the evaluation of U on the boundary of omega S. And G is going to be the evaluation of the normal derivative of U on the boundary of omega S. But it's helpful to define this via this family of diffeomorphisms so that the input variable here, Y, always lives in a fixed domain, which is the boundary of the original domain omega. This just sort of makes the analysis work out much more easily. So you always have a fixed domain. Okay, so basically F and G correspond to the trace of the solution on the boundary of the domain omega S. And you can do this and then write down a first order ODE, or first order dynamical system, for F and G. Okay, so I would call this sort of like a generalization of a spatial dynamical system to this multidimensional setting. And I mean, okay, you can of course just formally write down this equation. This function script F looks terrible, it's a huge mess, and it's not clear that you've gained anything. So the work here is in proving that this spatial dynamical system that you get is sort of well posed in some sense, and that solutions to that equation correspond in some meaningful way to solutions, to sort of weak solutions of the original elliptic PDE that you started out with. Okay, so this is a recent result that we have. So again, rather than sort of stating the theorem in its gory detail, I'm just going to illustrate the theorem in a picture. So what this result says is that there is a correspondence between weak solutions of your elliptic PDE on the original domain and solutions to this evolutionary equation describing the evolution of the boundary data on these shrunken domains. And the correspondence comes from this sort of trace map. Okay, and to state this result precisely, you have to state precisely what you mean by a solution to this spatial dynamical system. And then you have to prove that there's a correspondence between solutions of that dynamical system and weak solutions of the elliptic PDE. Okay, but you know, this then begs the question, what have we gained by doing this, right? Because we said, okay, we don't want to solve this elliptic equation, we'd rather solve this spatial dynamical system, but at least for me, it's very technical and it's not really fun to look at. It looks horrible and it's not clear that one can do anything useful with it. So what have we gained? Well, at least in the case where so I mean, if you're just given a bounded domain omega, you don't necessarily have a whole lot of control over how you're going to shrink the domain. You're restricted in some way. But if omega is all of RD, then you can choose to shrink the domain in whatever way you want. And so you can, for example, choose to shrink it in what seems like the simplest possible way, which is via spheres. Okay. And if you use spheres, then since the geometry there is relatively simple, the equation, your spatial dynamical system, does not look so bad. So the linear part of your dynamical system basically now just involves this Laplace-Beltrami operator on the sphere of dimension d-1. Okay, and this equation is not too terrible to think about. So this is still very much work in progress. But for example, from this sort of spatial dynamics point of view, what one might want to do is to start thinking about things like, does the linear part of the equation admit an exponential dichotomy? Can you use that exponential dichotomy to construct invariant manifolds for the system, and then think about intersections of those invariant manifolds, and when you have solutions to the nonlinear equation, all of these sorts of things. So this, and this is sort of the direction that we're going in now. So we have some preliminary results that tell us about when exponential dichotomies exist for the linear part of this equation, meaning if you ignore this function capital F. And this is very much related to work of Schiele and Sonstede and Schiele. So, you know, this notion of spatial dynamics, it's sort of, it feels natural when your spatial domain is one dimension, because then you have X is in one dimension. So when you write your system as a first order system, then X sort of naturally becomes a time-like variable. If you have a multidimensional domain, that analogy is still sort of natural. If you have, say, a cylindrical domain, maybe you have one spatial variable X that's infinite in extent, and all the cross-sectional variables are bounded. And so then there's a distinguished spatial direction that you can think of as the time-like variable, and then the remaining spatial directions you keep thinking of as just sort of cross-sectional directions. But if you're working on a bounded domain in RD, or something that doesn't have this sort of channel-like structure, it's no longer obvious what spatial variable or what variable you should view as the time-like variable. This work that I mentioned of Schiele and Sonstede and Schiele, they were interested in spiral waves on the plane. And so there they are sort of doing very much something similar to what we're doing here in the context of spiral waves. Okay, so yeah, so we're very hopeful that this sort of multidimensional spatial dynamics point of view will be helpful in thinking about multidimensional waves and patterns, not just stability, but existence, bifurcation, and things like that. But this direction is still very much new, and we still have a lot of work to do to sort of see what it will gain us. Okay, so let me just summarize. So again, we started out talking about Sturm-Liouville theory, which allows one to connect eigenvalues with conjugate points for scalar second order equations. And the Maslov index allows for a generalization of this correspondence to systems of equations in one spatial dimension and also to multiple spatial dimensions. And so many of the existing results, not just the specific ones I mentioned today, but also generally the other results that are out there recently connecting conjugate points and unstable eigenvalues via the Maslov index, many of the results are quite abstract in the sense that they haven't been used, to my knowledge, very few of them have been used to actually prove stability or instability of solutions, in particular PDEs. So that's why I find it notable that this result allows us to show that pulses in these reaction diffusion systems with gradient nonlinearities are necessarily unstable. So I'm very much interested in finding other applications for these abstract results. So if anyone has any suggestions or thoughts about that, I would love to hear them either right after this talk, or you can email me later. And then again, we're hopeful that some of the ideas used in the multidimensional case will lead to a useful formulation of spatial dynamics in higher space dimensions. So, okay, thank you very much. I think that's a great place to stop.